So welcome to the first of our Astrobiology seminar series for this quarter. As a bit of future advertising, next week we'll be having Dave Crisp from JPL talking about his new mission investigating, a new space mission investigating carbon dioxide levels and secret sources and sinks in the carbon cycle of the Earth. Very relevant to astrobiology because carbon fluxes are all important for regulating planetary temperatures. Of course, the other great volatile that's of vital importance to astrobiology is water, and this week's seminar will be on water and where it's not and why it's not on Mars, being given to us by Erika Harnett of Earth and Space Sciences, the Space Physics Group in Earth and Space Sciences at University of Washington. She comes to us from a physics background. She did her PhD here with Robert Wingley, investigating modelling of micromagnetospheres on the moon, and was the first to demonstrate the potential for such things by modelling. Subsequently to that, she was a postdoc of sorts in ESS, in the Space Physics Group, and has recently been appointed Research Assistant Professor in Space Physics. And her interests are generally in magnetospheric modelling and other such like processes. She'll be talking about Mars, where did all the water go? Erika.
Thank you. Yes, so I'm going to be discussing the sort of a space physicist take on where did all the water go at Mars. And I'll be presenting numerical simulations that will address what is the sort of some of the things we have to consider when looking at loss of water to space, and trying to figure out how much of the water was lost to space and how much of the water that was present on early Mars is still residing at Mars, possibly in what this picture has been interpreted as icebergs, dust-covered icebergs on Mars. So is most of the water in form of just being locked up at the surface and it's just not terribly visible, or did a lot of it leave and get lost to space? So I'm going to talk about some of the simulations, but first, though, that we're all on the same background, I want to give a sort of a short history of Mars and talk about some of the physical processes that could have contributed to loss of water to space. Remembering the geologic epochs at Mars is really easy because there's only three. The first one is the Nokian era. That one essentially is the era begins with formation, and the end of the era is associated with the end of heavy bombardment. This time is associated when water was thought to be fairly prevalent on Mars, and there would have been active erosion, there were possibly even lakes and oceans present. There would have been intense volcanic activity. There was a dynamo-generated magnetic field. When exactly that shut off is an area of active research and a big question. And impacts associated with heavy bombardment would have driven 80 to 95% of the atmospheric loss. The second era is the Hesperian era, and this is essentially the beginning of this era is associated with the end of heavy bombardment, and the end of it is a little fuzzy because it's associated when people think liquid water ceased to become stable on the surface. So we're not entirely sure when that's at. It's just sort of a general idea. And this is sort of a transition time from Mars going from having, in the early time of having a lot of active erosion, plenty of water, to the more arid time that we know of today. Any sort of water being prevalent on Mars would have been more episodic in nature. And the water would have been migrating, essentially migrating to the polar caps and underground. And there may have been transitional or episodic river activity. During this time, there may have been a resurgence of the dynamo magnetic field. That's a question. And most of the atmospheric loss that would have occurred during this time and water loss would have been through a more sort of a mass selective method. And to illustrate some of the episodic and breakout flooding, we see here, this is a picture of a fluvial fan that formed during this Hesperian era. And then the final era is the current era, which is the Amazonian era, which goes from this fuzzy time of when water stopped being prevalent to present. And this is an arid time. There's occasional breakout activity, but for the most part it's dry, dusty conditions, and there may have been occasional volcanic activity. But we do know that there is something actually happening, not just sort of in the short geologic time, but even on the very short time scales. This picture shows a crater wall, an image of a crater wall taken by Mars Global Surveyor, and the two images are the exact same spot 6 years apart. And you can already sort of see just from looking at this image that it looks like you see these crevices associated with some sort of flowing, possibly aqueous fluid movement. But the real kicker is when you look at the second image taken most recently is what looks like a new deposit. So even though the current conditions are not favorable for water, there does appear to be some sort of occasional transition activity. So just how unfavorable are the current conditions for water on Mars? This is the phase diagram for water. And the yellow rectangle here indicates sort of the range of current conditions that can be found on Mars. The highest pressures that are associated with the top of the rectangle are the conditions that would be found at the bottom of Valley Marineris during the summer. The pressures that you see at the bottom of the rectangle are the conditions if you're at the top of Olympus Mons. And you can sort of see that you have this little teeny spot right here where possibly you may get liquid water forming. That's why we do occasionally see it. The other thing that this graph points out is that in the past, if you wanted to have stable liquid water, just raising the surface temperature is not going to get you there. All you'll do is just transition from somewhere around here over to here. You're going to go straight from ice to vapor. In order to have stable liquid water on Mars, you needed to have more pressure in the past, which means more atmosphere. So what would that atmosphere have been? What was the past atmospheric condition composition possibly like? So what I've got shown here are the atmospheric compositions for the 3 terrestrial planets that actually have a thick atmosphere. I've left Mercury off here. And you'll notice by sort of just doing the top line comparison that our life-filled Earth is actually the oddball out in this comparison. That both Venus and Mars have primarily CO2 atmospheres. So if you think, well, okay, maybe if we use Venus as not having lost much of its atmosphere, then we could assume maybe that if Mars had a thicker atmosphere in the past, it would have been primarily CO2. But there was originally thought to be a problem with that line of logic. So if you use sort of a conservative estimate of what you might want to have for a thick atmosphere to have water minimally stable, you would assume maybe about 150 millibars of CO2. And just for reference, current conditions are about 7 to 8 millibars of CO2. The old conventional wisdom was that if you had a very thick CO2 atmosphere, you would get into a more favorable position on the phase diagram for water, and you would get a greenhouse effect associated with the CO2. But if there was a lot of water present, you should be generating carbonate rock everywhere. And there is very little carbonate rock seen on the surface. So this was thought to be evidence that the thicker atmosphere was not primarily CO2. Then Mars exploration rovers landed. Specifically, Opportunity landed in Meridiani Planum. And I'm sure we've all seen this absolutely beautiful picture of the layered outcrop at the top of Eagle Crater. And as MER got closer to this hot outcrop, it saw these little round rocks that have been termed blueberries. And just as a warning, this picture is a false color image and the blueberries are not actually blue. The blue color indicates composition, specifically that they're iron or hematite rich. And that was actually the reason why Meridiani Planum was chosen as a landing site. From space, it was indicated that there was a fair amount of gray hematite in that region, and gray hematite typically only forms in the presence of water. So that's why this site was chosen, and here it is, in the form of blueberries. When they got much closer, this is a zoomed-in picture of these blueberries. What these blueberries really are is something called concretions. They form when iron precipitates out of rock, when that rock is saturated with water. So they indicate the presence of water. And they're in every single layer of the rock layered outcrops that are in Eagle Crater. But more importantly, The surrounding rock around these blueberries is something called jarosite. Jarosite is a type of rock that only forms when the aqueous fluid has a pH of less than 5. And on Earth, it typically actually only forms when the pH is in a range of 1 to 3. So basically battery acid. So that water that was present when these blueberries formed, while there may have been a lot of it at times, it was very acidic water. And if you have a very thick CO2 atmosphere and very acidic water, you will not cycle the CO2 through the water and create carbonate rocks. So the thought that the atmosphere could not have been a thick CO2 atmosphere is now, that evidence is proven to be false. And with regard to life, one of the things this indicates is that if life was either developing at this time, possibly, or was already present, it would have had to deal with conditions that were not only very acidic, but oxidizing, saline, and intermittently wet. So with that sort of idea of where some of the past history of Mars, now I'll just talk about that through Mars's history, what are some of the loss or hiding mechanisms by which we can see water can sort of disappear from our view. So the first and most obvious possible hiding mechanisms is in the polar caps. And you can actually see from this picture I have up in the corner, this is a picture taken during the southern winter, and we see a very prominent southern polar cap. There's water, ice in the caps with a CO2 frost. And both the north and south polar, the persistent caps are about 3 kilometers thick. Another possible hiding mechanism relates to that picture I showed at the beginning, which is what had been interpreted as dust-covered icebergs, is it could just be locked up in permafrost or in the soil. And you could actually hide could hide tens of meters of water through that method. Or it could be lost to space. And we know that there has been loss to space because we have measured a significant amount of mass fractionization. Mass fractionization will only occur when you have something that's a mass-selective method, which only occurs when you're losing it to space, but with a caveat that you can modify it somewhat by the surface reservoirs. So with the sort of said, now I'm going to focus on the different types of loss mechanisms that can occur. And the first being a thermal mechanisms. So the first type of thermal mechanism is the one that was the primary loss mechanism, not only at Mars, but all of the early terrestrial planets right after formation, and that's hydrodynamic outflow. The early atmospheres would have been primarily light species, specifically hydrogen, and that species would have been hot. And as it was escaping, due to the fact that its thermal velocity had greater than its escape velocity and had enough energy, due to the fact that the atmospheres were very thick, it would have the collision timescales would have been very short, and it would have just dragged all of the other heavier elements with it. So this would have been this is a non-mass selective method. Another chief early source or mechanism for loss would have been impact erosion. Impactors occurring during the era of heavy bombardment. You get a vapor plume coming off of the impact. Vapor plume is essentially a small-scale version of hydrodynamic outflow. The temperatures are high, it's very thick, very collisional. The light species that are being lost will just drag the heavier species out with it. Also, it's a source of volatiles, so you get material back too. A mass-selective loss mechanism and thermal mechanism is thermal or Jeans escape. And this will occur once the atmosphere has become thinner, and then and your diffusion timescales are short compared to your collision timescales. In that case, you have species where the thermal velocity is greater than the escape velocity, such as hydrogen occurs now. They will escape, whereas if oxygen, it's gravitationally bound.
What's the distinction from the hydrodynamic? I thought that was also just normal heating.
It is, but the hydrodynamic escape, that one you have collisions. So the hydrogen, oxygen or something heavy may have normally, under normal conditions, have been its
dragging of the
exactly would have been below escape velocity, but the collisions will pull it out. So it's a collisional effect. Whereas when Jeans escape or thermal escape start taking over, the collision time scale is much longer, so you don't have hydrogen pulling the heaviers out. So it's just leaving and leaving behind a heavy atmosphere. So non-thermal mechanisms include photochemical escape. And this is actually a very important escape mechanism occurring in the current day atmosphere. And what occurs is you have CO2 will be ionized by ultraviolet rays from the sun, and in a fairly quick process, through photolysis, it will interact with an oxygen neutral, creating O2 plus and a CO neutral. This is the reason why CO2 is the dominant neutral at Mars, but O2 plus is the dominant ion at Mars. O2 plus can then interact with an electron and through dissociative recombination break apart the molecular bond and create two very energetic oxygen atoms. The star indicates that they're very energetic. This will create what's called a hot oxygen corona. These are very energetic oxygen. They escape very quickly and very easily from Mars and just make a corona of neutrals around the planet. This corona has been definitely measured up to 5 planetary radii away from the planet, and it's probably actually present up to 10 radii away from the planet. So this makes a very large corona around the planet. Another mechanism which then takes over is once you've got this neutral corona around the planet, there are ions coming from the sun in the form of solar wind, and there's magnetic field that's laced through that solar wind. It's still a very tenuous atmosphere, so the neutrals will not interact with the ions through collisions. And because they're neutral, they will not feel the effect of the magnetic field. But once they get ionized by solar ultraviolet radiation, they will instantly be picked up by that magnetic field. They will instantly feel it, and then start being carried downstream with the solar wind. And they can either just be carried downstream and go flying past Mars and be completely lost, or since it's a heavy element in the form of O+, they can re-impact the atmosphere, and they do so with much more momentum and energy than if it was a hydrogen ion. And in doing so, they can either break apart molecular bonds, or they can actually just kick heavies out of the atmosphere. If they kick the heavies out of the atmosphere, that's a process called sputtering. And this may have been an important process in the early atmosphere. And because we have ions that are interacting with the ionosphere near the planet at boundaries, there will be waves, plasma waves that will interact at that boundary. There's bulk removal or associated with this plasma waves, and instability can also lead to loss. So just to recap, the lost history at Mars is that at formation, the original atmosphere was delivered by impactors and outgassing from the created material. This hydrodynamic escape, which was non-mass selective, would then take over and stripping most of the early atmosphere until most of the hydrogen was gone. Then impact erosion would take over as the dominant loss mechanism until the end of heavy bombardment ended, but it would also lead to a source of volatiles. And then the wild cards come in that you have the secondary atmosphere that was there after the end of heavy bombardment may have possibly been protected by a global magnetic field and may have also been supplemented by some additional volcanic activity. And then genes escape and photochemical processes would then take over and become the dominant loss mechanism for neutrals and still be that today. And solar wind will have become the loss mechanisms, will become the dominant loss mechanism for ions. So what about this magnetic field at Mars? Up until the arrival of Mars Global Surveyor, it was not entirely known what the nature of Mars's magnetic field was. There was something measured, and it was weak, but nobody was quite sure if it was a weak global dynamo, or I've even seen papers where people thought, well, maybe Phobos, the moon Phobos, was magnetized, and that's what they were picking up. But with Mars Global Surveyor, they were able to prove, without a doubt, that the magnetic field that was being measured was actually in the form of magnetized rock on the surface. That goes by the name magnetic anomalies. And this is the first sort of measurement of these magnetic anomalies. The color indicates the magnetic field measured to be at the surface. It was measured at a higher atmosphere, so they don't know exactly what it is at the surface. Shown on top of a topography map. And because most people don't, except for space physicists, work in units of nanotesla, just as a reference, the Earth's global magnetic, dynamo-driven global magnetic field at the surface, at the equator, is 30,000 nanotesla. So only about 10 times larger than this. So these are very strong magnetic anomalies, which is why they was ambiguous. Nobody thought they could be quite this strong. Here's another showing of the because you couldn't really get an idea of where these magnetic anomalies were. This is a picture of the color indicates the topography of Mars, and the black and white contours indicate the magnetic field strength, both inward and outward. And you'll see that the magnetic field is primarily in the southern hemisphere and associated with this heavily cratered, older terrain of the southern highlands. But there are some magnetic anomalies in the northern lowlands and the newer terrain. Most of them don't show up on this resolution. They tend to be much smaller. And you also see that it appears that the large impact basins of Hellas and Arjar appear to be unmagnetized. The fact that Hellas and Arjar appear to be unmagnetized has been used to suggest that the Mars global dynamo turned off prior to the end of heavy bombardment. But it's possible that Hellas and Arjar are actually magnetized, but the signal is just so incoherent that it can't be measured at space. So it's not until we actually get something on the surface that measures, we couldn't know for sure. And the fact that there are magnetic anomalies up in the more newer terrain of the northern highlands, northern lowlands, has suggested to some that maybe the dynamo restarted later on in the Hesperian era. And then the other wild card that comes into this is the obliquity. Obliquity is the angle at which the rotation vector of a planet makes with the normal to the ecliptic plane. Currently, Mars's the obliquity angle is about 20 degrees. But simulations have shown that due to the fact that Mars only has two puny little moons, Phobos and Deimos, and does not have a large moon, its obliquity will have floated around and oscillated up to maybe even about 50 degrees up to about 10 million years ago, and possibly even more even earlier on. The fact that the Earth has a large moon has helped stabilize its rotation axis, so its obliquity rotates just a little bit, and is suggested that that's one of the actually helpers that made life on Earth a little more possible. So some initial results or research into what obliquity changes can do to Mars was by Manning, McKay, and Zelani, and they've looked at how obliquity changes would affect just variations in the atmospheric density, and showing this plot is just showing for a thicker atmosphere, which they claim is being 5 bars, so much thicker than we assumed earlier on, or a thin atmospheric model, so something less than 5 bars of atmosphere. How CO2 would have moved from being trapped in regolith and CO2 ice to being in the atmosphere, and found that if they started with a very thick atmosphere, the obliquity changes would lead to large changes in global warming and large variations in the atmospheric temperatures. But if they started with a thin atmosphere, that there wouldn't be quite as much variation. So with that background, I'll now talk about the solar-wind interaction at Mars. So this is a little cartoon of what happens, so I can define some of the terms. The solar wind is essentially the sun's atmosphere boiling off into space. And it's charged particles, so it's a plasma, so it's ions and electrons. There's no neutrals. As it's a plasma, it's highly conductive, and when it boils off into space, it will drag the solar magnetic field with it into space, and forming what's called the interplanetary magnetic field, or IMF. The inherent conditions are such that the solar wind, as it's traveling out into space, is moving with a speed that is faster than its inherent sound speed. So when it runs into an obstacle, such as a planet, like Mars or the Earth, and slows down, it will form a bow shock. And that's not well shown in this picture. As the kinetic energy is converted into thermal energy, it will form a hot layer of plasma called a magnetosheath, which is sort of shown in this region right here with a lot of wavy waves on the magnetic field. So the white lines in the magnetic IMF. Eventually, the solar wind will come in contact with the highly conducting ionosphere of a planet, if it's got an atmosphere, or in the case of something like the moon, it does not have an atmosphere. It will just keep plowing in. If it comes in contact with an ionosphere, because the magnetic field associated with the solar wind cannot transit through this conductor, it will pile up and then eventually slide around the side. So what are some of the solar wind possible solar wind conditions in the past from the sun? Well, we know essentially that a young sun is an active sun, and that in the past the ultraviolet and X-ray flux would have been larger. That would have led to more ionization of atmospheres, would have led to more heating. So an ionosphere would have been heated, it expanded, inflated, and increasing scale heights and expanding out this hot oxygen corona that Mars possesses. The solar wind would have been elevated. And by elevated, what I mean is that the density of material flowing off of the sun would have been higher or larger, and the speeds at which they come off would have been larger as well. That interplanetary magnetic field would have been stronger as well, but it works out that the pickup of ions in this corona associated with that would have actually decreased, though. And then we have our wild cards of when did the planetary magnetic field the global dynamo turn off, and how do obliquity changes figure into this. So one of the problems is if you're going to be modeling something, you want to have some data to validate your model against and prove that it's actually correct. We don't know exactly what the solar wind conditions were in the early sun. We can only look at solar type stars and estimate them. And we definitely don't have any data from that either. So the best thing we can do is use current day storms as analogs by which to test our models. So how good of an approximation is that? So I'm going to go through and talk about the four main characteristics of the sun for both storms, current day storms, and what we know from looking at solar type stars that are at least 1 billion years younger than the sun. So we know that the ultraviolet to X-ray flux was probably between 3 to 50 times larger. During a flare that's associated with a storm, the ultraviolet and X-ray flux can increase from 10 to 100 times its nominal range. The solar wind speed in the past was probably about 4 times larger than current values. During a storm, the speed will increase by about 2 to 5 times. Solar wind density was probably somewhere between 15 to 40 times larger in the past. During storm conditions, you can get dense increases in density that are about 5 times larger. IMF strength was probably about 10 times stronger at each given planet in the past. And during storm conditions, the IMF strength can increase by about 5 times.
IMF is what?
Interplanetary magnetic field, this magnetic field that's laced throughout the solar wind. Now, there's a caveat here. In the past, both the solar wind speed and the density would have been elevated. Typically, not all of the time, but typically, during a solar storm, when the speed increases, the density decreases. So they're usually inversely correlated. It doesn't happen all the time. So you have to be very careful with which storms you pick to use as analogs, because not all storms are created equal in that respect. So how do we do this modeling? We use something that we call a 3D multi-fluid model. The formulas that govern the physics of solar wind interacting with ionospheres and atmospheres of planets cannot be solved analytically. So we have to solve the set of equations numerically. And what we do is, we track several different ion species. For the most part, it's usually 3, one associated with the solar wind and 1 or 2 associated with an ionosphere of a planet or moon. And for each ion species, we solve conservation of mass, momentum, and energy equations numerically on a grid. Because we have this magnetic field that's both laced through the solar wind and maybe associated with the planet itself, we have to solve the induction equation. And then on a sort of large scale, we assume charge neutrality and a generalized Ohm's law as well. So what do some of the simulation results look like? So what you see here, this sort of blue blob with some green spots on it, is indicating Mars. The color variation is to indicate the fact that I have actually modeled the anomalous, put the anomalous magnetic field into the model. I'll talk about this a little bit more later. This is oriented such that the North Pole is up here, South Pole is here. Solar wind is coming in from the left-hand side, and the interplanetary magnetic field is arranged such that it's pointing into the board. And these give these are nominal, average, quiet conditions, solar wind conditions. So you don't have to worry about the numbers too much. What's shown here is the color is a log of the ionospheric density in a plane going through the noon-midnight meridian. So in fact, you can see North Pole here, so noon over here, midnight over here. The black contours indicate solar wind density. So this is actually tracking out this bow shock. How I've picked values so they pick out this bow shock. So this indicates where the solar wind comes in, and then the inner edge is sort of where it's sort of petering out. And one of the first things you sort of see is the ionospheric density and bow shock sort of track each other in the northern hemisphere. But in the southern hemisphere, there's a significant portion of ionospheric material that's outside of the bow shock. So this is basically in this unperturbed region where the solar wind is just traveling in as if there was nothing there. So why does that occur? It occurs because of the fact that ions in the presence of a magnetic field will gyrate in a circle about that magnetic field. And they gyrate in such that for this magnetic field, they will go in a counterclockwise direction. And if you were to launch an ion from the northern hemisphere, it would gyrate around and then re-impact the surface. But if you were to launch that same ion from the southern hemisphere, it would start gyrating around the magnetic field, and we would run into nothing. It would just go right out into the solar wind, where the conditions are different, and then this orbit about the size of the gyro motion would change. So anything sort of launched from here can then sort of bleed out in the southern hemisphere, can bleed out into the solar wind. And this is what's called pickup. This is the pickup region. Now, to run these, I did a series of simulations where I kept a single parameter the same. I either kept the solar wind conditions the same and moved the orientation of Mars, or I kept the orientation of Mars the same and varied a single parameter in the solar wind, just to figure out how ionospheric loss and solar wind precipitation into Mars's ionosphere changed with different parameters, because it's not a given that they would vary linearly. And to highlight that, I have sort of a series here. This indicates, or essentially nearly the same conditions as that first plot. So we have solar wind coming in from this side here, north pole of Mars here, south pole here. The color plane is running through the ionospheric density running through the noon-midnight meridian. The black contour lines indicate the bow shock. And this is sort of my nominal case, normal solar wind conditions. What we assume the primary ionospheric composition is of O2 plus in the ionosphere. When I only changed the mass of the ionosphere, so I went from O2 plus to O plus, the solar wind precipitation rate and the ionospheric loss rate both decreased by 30%. Now you think that might seem counterintuitive. If you decrease the mass of the ionospheric component, therefore its escape velocity should be lower, so you would think, well, maybe that it should have larger escape rates. What turns out to be more important is the fact that its amount of pickup actually decreases. And you can see that by comparing the southern portion here that's outside the bow shock. For this light ionospheric mass case, the pickup region is smaller. Because the pickup region is smaller, there is less loss. This goes back to the discussion of what was the past ionospheric composition. That was not just an interesting thought exercise. It is an actual important parameter to try to figure out, because it is crucial to get the mass effects right in order to figure out loss rates. And then when I started from the sort of nominal conditions and then merely doubled the solar wind speed, I saw that the ionospheric loss rates increased by twice, and again associated with this increased pickup. So the solar wind speed seems to scale linearly with loss rates, or the loss rates scale linearly with solar wind speeds. So I've been talking about the anomalous magnetic field. This is a picture of what it looks like in the simulation. So this is just purely magnitude, and it's at 400 kilometers, so higher than the picture I was indicating before of the surface fields. You can see primarily in the southern hemisphere, although there's a little bit of a strong one up near the equator. So this kind of comes down, do the ionospheric loss rates vary as a function of how the anomalies are oriented? If they're facing directly into the solar wind, if they're pointed sort of off to the side. This is important with respect to obliquity, because when the obliquity is around 50 degrees, these anomalies will never face directly into the solar wind. What I'm showing here is for four different cases for the solar wind, and where I ran with the anomalies pointed directly facing into the solar wind. So they were aligned along the noon meridian. What I'm showing is solar wind density at 400 kilometers. So what this means is when it's blue, the region is the anomalous magnetic field protects the region from the solar wind, and when it's red, it means it has an increased amount of solar wind penetrating into that area. And you can see that when I just merely rotated the interplanetary magnetic field by 90 degrees, the protected regions sort of moved around a little bit, and some of the enhanced regions moved around. But there are also still regions where that were protected from one IMF orientation remain protected from the solar wind, and regions that were enhanced for one orientation remain enhanced. So places you probably don't want to build a Martian base. And then when I went to sort of more active storm, old sun type conditions, everything sort of gets smeared out, but you still have regions that are a bit protected. The main thing I found was that the loss rates didn't seem to vary much with anomaly orientation. Now that could be because whatever plasma was deflected from, say, this region was just funneled to another region. So when you calculate things globally, you didn't see a net change because they were just moved around. Another possibility was the fact that the sort of grid type, the sort of bar-shaped pattern or barcode type pattern associated with the anomalies was actually on the order of the grid resolution in the numerical simulations. We have to solve our numerical simulations on a grid, and they were about comparable. So it was possible that I was maybe just not resolving the anomalies. So it didn't really. So even though this made it look like they were there, they really didn't look like they were there in the simulations. So in order to resolve this issue, where there was just moving plasma around, or this effect wasn't resolved, I did higher resolution simulations of the solar wind interaction. And so what we see here is this sort of sphere, colored sphere is again Mars, and the color indicates the magnetic field. And you can see up in the sort of close to the equator, this sort of region of high magnetic field that I pointed out earlier. The really strong anomalies are down here closer to the southern hemisphere, and you can't see them because they're off plane. The colored material, or the colored planes here, are either solar wind density, ionospheric hydrogen density, or ionospheric oxygen density in the noon meridian, and then also showing magnetic field lines. And you can see that you can definitely see sort of features associated with anomalous magnetic field, and you see sort of this loop-like structure where it's just this pure anomalous magnetic field and is protected from solar wind. So very low solar wind density and higher ionospheric density in those regions. And then there's this region down here where the interplanetary magnetic field sort of connects to the anomalous magnetic field and almost sort of funnels solar wind into that region. So you see higher densities here of solar wind. And in that region, you're sort of essentially seeing where the ionosphere, or the atmosphere of Mars, has been eroded or eaten away by this increased solar wind access. So when I went through and did higher resolution simulations, I found these are ionospheric loss rates of the different components, both O2 plus and hydrogen, and then solar wind precipitation rates for nominal conditions, but different orientations of these strongest anomalies. Ones where they were located on the dawn terminator, or if they were located on the dusk terminator, or if they were located at midnight. And now you can see significant variation with anomaly orientation. And these numbers work out to being, for these nominal conditions, of about 2 to 3 times 10 to the 25 ions per second, correspond to being over 1 billion years. That would be equivalent to 10 centimeters globally of water lost from Mars. For more storm-like conditions, which I'm not showing the numbers here, this increases up to about 10 to the 26 ions per second, and that would correspond to over 1 billion years being able to lose a meter of water globally to space. So what are the conclusions from my interactions? Is that due to solar wind interactions alone, you could possibly, over the lifetime of Mars, lost meters of water to space. And one of the things that's important for figuring this out is to try to get some limits on the composition of the early Martian atmosphere. As we saw, the loss rates correlated fairly heavily with the mass that you assume for Mars. Another thing, so that the composition is quite important. Another thing I think is that when you can resolve them, when you're able to simulate properly, the loss rates do correlate with the orientation of the magnetic anomalies. So this means that it's really actually, you do have to pay attention to obliquity changes, because there are times when those anomalies may not face into the solar wind, and therefore your loss rates during those periods will have changed. And that's pretty much all I have.
Any questions?
So what's the current best estimate for the amount of water remaining on Mars? Like, for example, in the camps?
It's probably tens of meters. So it's in the tens of meters that have been lost.
So
but nobody knows how much there probably was.
Yeah.
Because so the question is, was there enough to completely fill that northern lowland? Some people like James Head have looked at high-resolution images and have suggested that and sees what he thinks is evidence for seashores and wave action around the edge of that whole northern lowlands. So as his suggestion is, there were times when that entire region was filled with a lake, a giant lake, or an ocean. But nobody knows how much water would have been moving around at the time.
We have a question from Penn State.
Early accepted that there was one.
Yeah. Hi, Erika. This is Jim Casting. In the beginning, when you went through the list of escape mechanisms, you talked about hydrodynamic escape, and you mentioned that it is non-fractionating.
I know there have been people who have suggested that maybe a lot of what we associate with being water has actually been due to wind or aeolian processes. I don't know if that's really how well resolved that is. I mean, we do know that there's water there, so I don't know.
That first photograph came after there was one jury, but it don't stand in front of the fan when it gets hit by the evidence that it's not water. My Finnish colleague, I work on Mars missions with him, said, we see those in the Alps all the time when you're climbing the airport. It was landslides. That's very common.
Okay. Yeah, it's not showing what they are. Some people have suggested that there was some sort of explosive process that may have explosively ice or vaporization. It's still open for debate. Yeah, I agree.
I keep doing something about water, and I couldn't conjure up anything except a meteorite or something that exploded.
Yeah.
You can't make liquid water sit close to the surface very well.
Yeah, it's thought that a lot of the current transition or events may be associated with impacts of some sort.
We have a couple of questions from the ether.
So Penn State has a question?
Okay, sorry. Erika, in the beginning, when you were talking about hydrodynamic escape, you mentioned that it was non-fractionating. There's actually a couple different regimes in there. I mean, what we call non-fractionating escape is often termed blow-off. There's also a regime of hydrodynamic escape that is fractionating, and there's a long literature. Bob Pepin has written lots of papers on this.
Okay.
So some loss may occur by that mechanism. In fact, we think that would be very important early on.
No, thank you for pointing out that there are two types. From some of the stuff I've read, it suggests that also that some of the early mechanisms were not quite as mass selective as things that would have come later on.
But in fact, Bob Pepin has derived this whole history of the solar system doing the fractionation of noble gases and noble gas isotopes using hydrodynamic escape. So that it may be part of the picture.
Okay, thank you.
Okay. Any more questions from here? Yes, Darcy.
Can you talk a little bit about why, I guess certainly just why Venus still has a really dense atmosphere, Mars doesn't? And can you say much about the original atmosphere? Venus has kind of a constantly replenished
There are a couple of things that I don't know a lot about Venus, but I know there are a couple of mechanisms that I mentioned. Venus doesn't have one of these hot oxygen type coronas because even after the process of photolysis and dissociative recombination can occur, but at Venus, the hot oxygen that is created after the dissociative recombination is still below escape velocity. So Venus doesn't have a hot oxygen corona. So it doesn't have this large material. Therefore, it won't have the sputtering and some of the pickup processes. And so I think that's one of the reasons why it may have held on. It's also more massive, so its escape velocity is a lot higher. So conversely, it's also closer to the sun. But I think that the more massive amount, more mass does help retain more of the atmosphere in that respect.
Any more questions, comments? If not, I'd like you all to join me in thanking Erika.